Welcome. This is our Chapter 3 exam practice, page number 3, and question 9. The noon temperatures in Fahrenheit for 2 cities were recorded over a given month, and we have side-by-side box plots summarizing the data. All right, so in our box plot, just a reminder here that left whisker would go down to the lowest value in the data set, and then left side of the box is the first quartile, also called the lower quartile. And then the line here in the box is the second quartile, which would also be the median. And then the right side of the box is the third quartile, also called the upper quartile. And then the highest temperature for city A here would be that value. Oops, I usually don't call it U for upper, the H highest, the highest temperature. Okay, and so we have information there about city A, city B, and it says find the range for city B. So range is the difference between the highest and lowest value in the data set. So essentially whisker to whisker, we want to know the spread. All right, so I'll put the number above it here as well. It looks like that right whisker goes to 85 and the left whisker goes down to 73. So 85 minus 73. And that will be a difference of 12 degrees. So I'm not going to write units the whole way through, but we are talking about temperature. So the spread there, 12 degrees Fahrenheit. And I'll just put the units there and go to B. All right, so find the interquartile range. So we did range first and now interquartile range. And that formula, we abbreviated there IQR. That's the difference between the third quartile and the first quartile. So that's basically the length of the box. And we're going to do that for city B. So it looks like the third quartile there is 83. And the first quartile at 75. So substituting, we would have 83 minus 75. And that will be a difference of 8. All right, and like I said, I won't write the units again here. Just wanted to emphasize that we do have units involved, and we'll go to C. So we have our range of 12, interquartile range 8, and then we're asked to describe shape of the distribution for each city. All right, since we just talked about city B, I'm just going to do that first. So this is a perfectly symmetric shape. It doesn't even have to be perfect. If it's something close to symmetric, we would identify it as symmetric. Left side of the box, same as right side of the box in terms of length, and left whisker and right whisker the same length. So down here for city B, that distribution would be called symmetric. And then back to city A. So for city A, right whisker longer than left, right side of box longer than left side of box. And that creates our skewed right shape. So that one is skewed right. So not every graph has a shape, but these certainly do. And that would also be called positively skewed. So either way, skewed right or positively skewed. And then finally D, which city had the higher median noon temperature? All right, median. So that value for city A is there. And then for city B, it is higher up the number line there. So city B had the higher median. All right. And then we'll move on here to number 10. So number 10, we have scores on a standardized test follow a normal distribution. So that's our bell-shaped curve where most of the data is in the center of the graph, and then it tapers off in terms of number of data values as we go to the left and right of center. All right, and they tell us that the mean on this standardized test was 72 points with a standard deviation of 8 points, and we'll let X represent a score on the test. So let me start by identifying the parameters. So population parameters were provided, mean 72, and the symbol for the population mean is mu. And then standard deviation 8, and the symbol for population standard deviation is our lowercase sigma. And then for part B, we'll use the empirical rule for bell-shaped data to label the relevant percentages and test scores on the graph. All right, I'm just going to come over and make my graph a little bigger here. I'm going to label my x-axis. So x would be points scored on the exam. And the mean was 72, and that establishes the center of the distribution. All right, so that's your mean. And then the spread of the distribution is established by the value for sigma. So what we're going to do is move one standard deviation left and right of the mean. And we're actually going to go 3 times to the right and 3 times to the left by adding sigma. So our sigma was 8. So 72 plus 8 would bring me up to 80. And I'm going to go this way first and just do this middle part. So 1 standard deviation from the mean. If we add or subtract 1 standard deviation, so 72 minus 8 brings me down to 64. And the empirical rule for bell-shaped data says that if we look at all the data and the scores between a 64 and 80 points, that's going to be approximately 68% of the data. So I can now tell you where 68% of students scored, somewhere between a 64 and an 80 on the standardized test. All right, so let's go another standard deviation in each direction from the mean. So we added 8, that's 1 standard deviation. Let's do it again, add another standard deviation, and that's going to bring me up to 88. And then I'll go another standard deviation below the mean. So we will subtract 8. So 64 minus 8 brings me to 56. And the empirical rule for bell-shaped data tells us that between 56 points and 88 points, that would be approximately 95% of the scores on the test. All right, one more time here. We're going to go another standard deviation from the mean. So we'll go above the mean, add another 8. That brings me to a 96 point. And then subtract another standard deviation. And 56 minus 8 is 48. So between 48 points and 96 points, that's really almost everybody that took the test. That's going to be 99.7% of scores. All right, and there is your graph of the empirical rule for bell-shaped data with those particular parameters. And then we'll be able to answer some questions here. All right, approximately 95% of test scores are between. So 95%, that would be people that scored within 2 standard deviations of the mean. So from the mean, 2 standard deviations below, 2 standard deviations above. So they are within 2 standard deviations of the mean, and that will be 56 and 88 points. All right, approximately what percentage of scores are between 48 and 96? So there's our 48 and our 96. So between 48 and 96 would be 99.7% of scores. All right, and then I'm going to talk about Chester here. So Chester was among the test takers, and Chester scored 94. So Chester is out here, and we are going to find his z-score. All right, so let me just first document his data value. So X represents a score, and in this case, Chester's was 94. And we're going to convert that to a z-score by using the formula z equals. So the z-score is the data value minus the mean of the population. And then we divide that by the standard deviation. All right, so Chester had a 94. The mean of the distribution was 72. And we'll divide that by our standard deviation, sigma, which is 8. And then be careful with order of operations. You want to get that numerator first, and that is 22. And then you can divide by 8. Oops, sorry, I hit that twice, but it's up there, 2.75. So it's a positive z-score because his score is above average. So interpretation, Chester's score was, so he was 2.75 standard deviations above the mean. So the z-score tells you how many standard deviations a value is from average from the mean. All right, and then we'll move on to Chloe here. Chloe was among the test takers, and Chloe scored a 60. So X is 60. And again, z-score. So z-score is X minus mu over sigma. And I can see here that Chloe, here's the mean. If Chloe got a 60, she's down here somewhere. So her z-score will be negative. So just as a reminder here, for z-scores, the mean is 0. Negative z-scores put data below the mean, positive put data above the mean. So let's find Chloe's z-score. Okay, so Chloe first, X, and then we subtract the mean of the population, 72, and divide by standard deviation of the population. Okay, let me just get on the calculator there. All right, so don't forget numerator first. So 60 minus 72 is negative 12. So she's below average, and dividing that by the standard deviation gives us negative 1.5. All right, so her z-score is a negative number, but when we speak, we're going to talk about how many standard deviations she is from average. So when we speak, we'd write a positive there. That's how many. She's 1.5 standard deviations, and then we would indicate that she is below the mean, below the average. All right, then hopefully that helps a bit with page 3.